Hello. In this lesson, we're going to look at motion along a curve. Now, in our previous lesson, we were talking about motion along a line, so strictly horizontal motion or strictly vertical motion, for example. But with motion along a curve, we're going to see that it's possible to have both horizontal and vertical motion happening at the same time. So we're going to look at problems that involve planar motion or motion in a plane. And to do that, we're going to use something called a vector-valued function. So let's recall the definition of a vector. And one way that you can define a vector is just as a directed line segment, right? It has a finite magnitude or length, and it has a specific direction. So directed line segment. And there are different notations that you can use to describe vectors, but the one that we're going to be using here is what we are seeing right here. So it's almost like writing an ordered pair, but we're using angular brackets instead of parentheses. Now, every vector has an initial point and a terminal point, right? So here's our initial point, and here's our terminal point. If we know it's in standard position, we know the initial point is at the origin, then all we need to know is the terminal point in order to figure out which vector we're talking about. So we have this convenient notation. Whenever you see this notation here with the angular brackets, and you've got v1 comma v2 inside, the v1 comma v2, those are giving you the coordinates of that terminal point. These are called the components of the vector. So we have an x component, which is describing the horizontal distance from the origin to the terminal point. And then we have the y component, which is describing the vertical distance from the x-axis and the terminal point. So the individual components here, this v1 and this v2, those are real numbers, and we call those scalars. But overall, we call this, when we put the angular brackets around those components, we call this a vector. Okay, so that is vector v. And it has components v1, v2. Horizontal component v1, vertical component v2. Now, instead of using scalars as our components, we actually used functions to determine the value of the components, then we're creating what's known as a vector-valued function. For example, if instead of saying that vector r is equal to the vector in standard position with components 1, 2, right, that is fixed. There is only one vector that is in standard position and terminates at the point 1, 2. So that vector right there is unique. But if instead of just a 1 as the x component, we actually have a function there, a function of t like we see below, where here r of t equals the vector with x component f of t and y component g of t, now we have a vector-valued function because those functions, f of t and g of t, are being used to produce vectors. They're not producing just real numbers, they're generating vectors. So if we think about this, we really have sort of three variables at play here, right? We've got t, which is the input for the function f and the function g. So t is a variable, and the value of t is going to determine the value of f. It's going to determine the value of g. So f is changing based on the value of t, so it's a variable. G is changing based on the value of t, so it's a variable. We've got three variables here. We've got our x component, which is determined by t, and our y component, which is determined by g. So f and g and t, three variables at play here. So hopefully this sounds somewhat familiar. We started this unit looking at parametric equations, and in parametric equations, a similar thing sort of happened. We had a variable x and a variable y, and each one of those were defined in terms of t. So we're sort of bringing together now parametric equations along with these vector value functions. Now, we saw when we were working with parametric equations that if we plotted points using increasing values of t, we were able to see the orientation of the curve. And a similar thing is going to happen here. If we increase our value of t and imagine like each vector as that's happening, which all of the vectors that are being created as we change the value of t. And if we use increasing values of t, we're going to see the path of the terminal point as it's traced out in space. So we're also going to get an orientation here. So in the image we're looking at, the vectors are, of course, what you see in orange. And if we say that this is our lowest value of t right here, maybe that's t naught, and maybe this is t sub 1 and t sub 2. And of course, in this example, these vectors are very spaced apart, but really we can, we would use t values that were so close together that we would actually trace out the path of this curve. And we can see then the curve that is being traced out is the one that is in dark blue, and the orientation here is coming in like so. So this is giving us a way to really trace out a curve in three-dimensional space. In this problem, we are given the equation of a parabola, y equals x squared plus 1. This is an equation in rectangular form, and we're asked to rewrite this equation as a vector-valued function. So I want you to pause here for a moment and think about what needs to happen, or what do we need in order to write this as a vector-valued function. Remember, our vector-valued function has two components, an x component and a y component. And each of those components is a function defined by some other variable, which we can call t. It's not necessary to call it t, but let's just go ahead and call it t. So think about that for a moment and see if you can come up with a vector-valued function to represent y equals x squared plus 1. Well, if we are able to come up with a pair of parametric equations for y equals x squared plus 1, then we're almost there. After that, it's just a matter of using the right notation. So how would we write this as a set of parametric equations? The easiest way to convert a rectangular equation into a parametric equation is to either choose x and let that equal t, or choose y and let that equal t. So in this case, it would be easier to just let x equal t. We have x equal t. And then once we've decided that, we can just substitute t in for x, and we get y equals t squared plus 1. Now, this isn't a vector-valued function yet. This is just parametric equations, but we can very easily write this in the form. And I don't necessarily have to use function notation, but just so we match what we saw a moment ago on the previous slide, we can write this as x of t equals t, and then y of t equals t squared plus 1. We could even switch to f of t equals t and g of t equals t squared plus 1. But all we need to do here to write this as a vector-valued function is to put it in that component form. So our x component first, followed by our y component, and then we can use angular brackets to indicate that this is a vector-valued function. Here we're asked to sketch the planar curve represented by the given vector-valued function. So we have vector r of t has x component 2 cosine t and y component negative 3 sine t. And we're only working on the interval from 0 to 2 pi, the closed interval from 0 to 2 pi. So we're given a hint here on how to get started. We can write a set of parametric equations and eliminate the parameter. By doing that, we're going to rewrite this vector-valued function in rectangular form. And I'm guessing it's going to be something that we would recognize when we look at that equation. So parametric equations, we know we can just say x equals 2 cosine t, y equals negative 3 sine t, and how are we going to eliminate our parameter here? We're going to use some trig identities to help us. If we isolate the cosine t in the first equation and isolate the sine t in the second equation, this is going to be easier. So we can say x divided by 2 equals cosine t, and then y divided by negative 3 equals sine t. And which trig identity can I use here now to eliminate this parameter t? Well, if we square both sides of these equations and then add the left-hand sides and then add the right-hand sides, we'll maintain equality. So we'll have x squared over 4 equals cosine squared t. In the next equation, I'm going to have y squared over 9 equals sine squared t. I'm going to add those left-hand sides. So x squared over 4 plus y squared over 9 equals cosine squared t plus sine squared t. And of course, we know cosine squared t plus sine squared t is equal to 1, leaving us with x squared over 4 plus y squared over 9 equals 1. Now, if the denominator here in this first fraction and the denominator in the second fraction were equal, then we would have a circle. But because they're not equal, and we do have a positive x squared and a positive y squared, this is an ellipse. Okay, for this ellipse, we have the larger value, the 9, is under the y squared. So I know this one has a major axis parallel to the y-axis. So here, if we're thinking about the standard form of an ellipse, our a value is 3. The center for this ellipse is 0, 0, because we can think of this as x minus 0 squared and y minus 0 squared. So our ellipse is centered here at 0, 0. And then major axis, from that center point, we're going to go up 3, down 3. And that's going to give us our vertices. And then we can look at our b value, which is 2. It's the square root of 4, so 2. And again, from the center, we're going to go right 2, and we're going to go left 2. And now we can see where we have that minor axis. And I will do my best here to draw this ellipse. I usually have to kind of just do dotted lines first. It gets really wonky. Still not looking so great. But we've got an ellipse. And just because I'm drawing it in this direction doesn't necessarily mean that's the orientation. But we can check our orientation by going back up to our original vector valued function here, and then just plot 2 points. Hopefully we can get it in 2 points. Plot using increasing values of t there. Okay, so let's try t equals 0. At t equals 0, we have our x component, 2 times the cosine of 0, so x equals 2, and our y component, negative 3 times the sine of 0, so that would be 0. 2 comma 0, that is this point right here. And now I'm going to choose a slightly larger value of t. I don't want to go too large, but let's try pi over 2. T equals pi over 2. So t equals pi over 2, x equals 2 times the cosine of pi over 2, 0. Y equals negative 3 times the sine of pi over 2, which is negative 3. So my next point is 0, negative 3, this point down here. So now I know that the orientation is going this way. Here we're going to look at some operations that we can use on vector valued functions. And we've seen operations like these before in different contexts. Number one, that sum difference rule. We've seen this with derivatives. We've seen this with integrals. We've seen this with summations. And we're seeing it here with vector valued functions. So basically on the left-hand side of this equation, we have 2 separate vector valued functions. And on the right-hand side of this equation, we have a single vector valued function. So we're able to put the 2 on the left together and make it just one vector valued function here. And we do that just by adding the x components and then adding the y components. If the 2 vectors are being added, or if they're being subtracted, we subtract the two x components and then subtract the two y components. So it's pretty intuitive how that one works. And then the second operation here, we have a constant multiple by our vector valued function. So that c right there is a scalar, or it's what we call constant multiple. And we see that we can simply multiply that scalar by each one of our components. Multiply it by the x component, multiply it by the y component, and now we've put it just inside of that vector valued function. We can also work backwards here. If we have a vector valued function and they both have a common scalar multiple, that we can factor it out and remove it from the vector valued function. Okay, let's look at the example before or below. We have two vector valued functions, r1 of t, r2 of t, and we're asked to find r1 minus r2. So we're going to write this as a single vector. We can use our angular brackets to denote that this is a vector valued function, and we will subtract our x components, so t squared plus 1 minus 3t squared. And then for the y component, 2t minus t minus 4. Now we can simplify that, and we have an x component, so t squared minus 3t squared is negative 2t squared plus 1. That's our new x component. And then the y component, we have 2t minus t, or just t, and then minus 4, it's going to be plus 4. And for 4 times r1 of t, we're just going to multiply that scalar to each one of the components for vector r1. So it would be 4 times t squared plus 1 for the x component, and then 4 times 2t for the y component. And we can simplify that, 4t squared plus 4 as our x component, and 8t as the y component there. And now on to the calculus. So how do we take the derivative of a vector valued function? Here we're given a vector valued function, just r of t equals the vector with x component f of t, y component g of t, where f and g are differentiable functions of t. And we see that the derivative of our vector valued function is just given by the derivative of the x component and the derivative of the y component. Let's look at some examples. So in each of these examples, we're given a vector valued function r of t, and we're asked to find r prime and then r double prime. So to find r prime, you're literally just going to take the derivative of each component. It's pretty straightforward. R prime of t equals, then we just need the derivative of 6t, which is 6, and the derivative of negative 7t squared, which is negative 14t. For our second derivative, we're just going to take the derivative of the components of our first derivative. So the derivative of 6 is 0, and the derivative of negative 14t is negative 14. So our second derivative here has constant components. Okay, go ahead and pause here and see if you can work out number 2 and number 3. For number 2, we're going to start by taking the derivative of our x component, the derivative of the square root of t. So we can think of this as t to the power 1/2 there, and negative t to the power 3/2 over here. Derivative of t to the 1/2, we're just using our power rule, 1/2 t to the negative 1/2. And then derivative for negative t to the power 3/2, negative 3/2 t to the 1/2. And if we want to clean that up a bit, we can say that is 1/2 root t and negative 3 root t over 2. Now that was just our first derivative. We still need to find our second derivative. So we have r double prime of t equal to, And here we probably want to use this version of r prime so that we can apply that power rule more easily. So I'm looking up there when I find my derivatives here. -1/4 t to the -3/2, and then -3/4 t to the -1/2. And if we want to rewrite those so that we don't have negative exponents, we can do -1 over, and we can leave it with the rational exponents, 1 over t to the power 3/2. Or if we want to switch to radical form, that's going to be the square root of t cubed. And here, -3 over 4 root t. Okay, I'm going to erase that so we have room to work out number 3. And number 3, in order to take the derivatives here, we are going to have to use the chain rule. So to find r prime of t, we're going to take the derivative of cosine cubed t. So I'm thinking about that as if it were written like this, the cosine of t cubed. So we've got stuff cubed. When you take the derivative of stuff cubed, you get 3 times stuff squared times the derivative of the stuff. So we need 3 cosine squared t times the derivative of cosine t, which is negative sine t. And that is our x component. For our y component, we're taking the derivative of sine squared t, and I'm thinking of that as the sine of t squared. So again, I'm using chain rule here. This is stuff squared. The derivative of stuff squared is 2 times stuff to the power 1. So 2 times the stuff to the power 1 times the derivative of the stuff. And the derivative of sine t is cosine t. Okay, there's our first derivative. Now we get to move on to second derivative. To take the derivative of -3 cosine squared t sine t, we need to use the product rule and the chain rule in order to take the derivative of the cosine squared t part. Okay, so product rule. When I'm doing product rule here, I'm thinking of grouping it like so. All of this is my first factor, and then sine t is my second factor. And I am saying to myself, what is the derivative of the first? Okay, so the 2 comes down in front, and it's -6. Cosine to the power 1, cosine t, times the derivative of cosine, which is negative sine. So that becomes a positive sine t there. So all of that is just derivative of my first factor. I'll erase that leading plus there. So this is derivative of first times the second. So times sine of t, which makes that a sine squared, plus the first, -3 cosine squared t, times the derivative of the second, and the derivative of the second is cosine t, so we are going to make that a cosine cubed right there. That is the derivative of the first derivative, so that becomes my new x component here. Now for the y component, we have to take the derivative of 2 sine t cosine t. And we have some options here. We can use the product rule, like I did for the x component, just use the product rule. We don't even need chain rule on that one. Or we can use a trig identity here and say, oh, 2 sine t cosine t. I know that that is equal to the sine of 2t, and that's actually a simpler derivative to take rather than having to do product rule. So I'm going to choose to do that. And the derivative of sine of stuff is cosine of stuff times the derivative of the stuff. So there is my y component. So we've looked at how to find the derivative of a vector-valued function. We can also integrate a vector-valued function. If r of t, the vector r of t, equals the vector with x component f of t, y component g of t, where f and t are continuous on the closed interval from a to b, then the integral of vector r of t is found just by taking the integral of the x component and the integral of the y component. If we need a definite integral, then we will integrate on the interval from a to b. So again, pretty straightforward. Let's look at these examples. So the first two, indefinite integrals. Number 3 is a definite integral. We'll start with number 1. Pause for a moment and just see if you can figure out what it is, just by, what you already know about integration. Okay, for number 1, we're going to integrate this x component 3t squared, and when we do that, we get just t cubed. Well, I shouldn't say just t cubed, because it's not just t cubed. If we integrate 3t squared dt, we get t cubed plus c. And that's going to be our new x component here. Now we can integrate our y component. If you integrate 4t, you get 2t squared plus c. Now, is there a problem with the way that I wrote that? The way that I wrote that, it looks like this value and this value are the same value, but they don't necessarily need to be the same value. So we can't call them both c. We're going to have to distinguish them from one another. You can use a different letter, maybe call one c and call one d, or you can use a subscript. You can say that's c sub 1 and that's c sub 2, or if you like, you could say c sub x for the x component, although we don't want to confuse it with the variable, it is a constant. So this is our new vector valued function, and it is the integral of the original vector valued function. Number 2, again, we're just going to integrate that x component. So the integral for 1 over t dt, ln absolute value t plus c1. And then integral for ln t. Now the integral for ln t, that's one that I just have memorized. It's not an easy one to remember. If you don't remember it, we have worked this one out back when we first learned integration by parts. So you can integrate ln t dt using integration by parts. But I already happen to know that the integral of ln t dt is t ln t minus t plus c. And this one will be ac2. Now it does seem a little strange that when we integrated the x component, we had to use absolute value around our t. And when we integrated the y component, we did not. But remember why it is that we're using absolute value around the t there. The domain for 1 over t is all real numbers except 0. Right here, the only restriction on t is that it cannot be 0. But when we integrate it, if we don't write absolute value, then when t is anything less than 0, we run into a problem. Right, this function, or if we didn't have absolute value, let's say, if we just wrote ln t, this function here does not have that same domain, right? This is positive values only for t. But by using absolute value, we preserve the domain. This one has a domain of all real numbers except for 0. So we're preserving that domain there. Versus when we start with ln t, we already have a restriction on our values of t here, telling us that t must be greater than 0. So when we integrate it and we write t ln t, we already have that restriction in place that t is greater than 0. So we don't need to make any modifications there. And number 3, so this one is a definite integral. How are we going to handle definite integrals? Well, let's just start by integrating and see where that leads us. So we integrate the x component, and we're going to get 4t squared plus c1. Integrate the y component, and we're going to get t squared over 2 plus c2. And we need to evaluate this from 0 to 1. I actually don't know if this is proper notation. I'm just kind of going by how it was on the left. It does look a little funny, but we know how to evaluate this definite integral. First, we're going to sub in our upper limit of integration, so the 1 in for the t, and then we'll sub in the 0. Now, I'm just going to go ahead and work entirely with the x component first. Yeah, maybe it would make more sense if I had written that in a different way. I don't know that this notation is wrong necessarily. It just does seem kind of weird. So let's move that to the inside. And we can do this from 0 to 1, and then this from 0 to 1, because really that's how I want to evaluate it anyway. Okay, so just working with our x component now, if I substitute the 1 in for the t, I just get 4 plus c1. And because this is a definite integral, we know from experience that this c1 is just going to cancel out. It's just going to cancel out, because when I substitute in the 1, I would have 4t squared plus c1. And when I substitute in the 0, oh, that's not a plus. That should be a minus. When I substitute in the 0, I'm going to have 0 plus c1, and the c1s are going to cancel out. And that's always going to happen. So you can get away with just not even writing the constant term there. And, you know, if it's a definite integral only. Obviously, don't do that if it's an indefinite integral. But since it's a definite integral, we can ignore that constant there. So let's try that again. Okay, sub in the 1, we get 4, minus sub in the 0, we get 0. And then for our y component, we'll sub in the 1, and then minus sub in the 0. And our vector is 4, 1/2. So our definite integral here gives us just one specific vector with a constant x component and a constant y component. In this problem, we have a vector valued function, r prime of t, x component 3t squared, y component 6 root t. Find r of t. So we're given the derivative, and we're trying to work backwards here and undo that derivative. What was the vector that produced, or whose derivative produced, this 3t squared 6 root t? We're also given an initial condition. We know that the vector r, when t is 0, is equal to the vector with components 1, 2. So let's start by integrating r prime to get an equation for r. And we can say vector r of t is equal to, we'll integrate 3t squared to get t cubed plus c1. And we'll integrate the 6 root t, so I'm thinking of that as 6t to the 1/2. Integrate, and I get t to the 3/2. Dividing by 3/2 is the same as multiplying by 2/3. So that would give me a 4 in front there, plus c2. And that's our function r of t. Now we can use this initial condition to solve for c1 and solve for c2. We know that the x component is supposed to equal 1. So we can say t cubed plus c1 equals 1 when t equals 0. So actually, it should say 0 cubed plus c1 equals 1. Therefore, c1 equals 1. So t cubed plus 1 for the x component. Now for the y component, we know that when t is 0, the y component is supposed to equal 2. So 4 times 0 to the power 3/2 is just 0, plus c2 is equal to 2, and that means c2 equals 2, giving us the y component for t to the 3/2 plus 2. Okay, so let's pause here a moment and see if you can do number 2 on your own. In number 2, we start with a second derivative, and we have to find just vector r of t. So if we integrate r double prime, we're going to get r prime. And if we integrate e to the 2t, this requires a u substitution, but it's one where we can take a mental shortcut because the derivative of the u is a constant. So the integral of e to the 2t dt is e to the 2t divided by 2 times the 8, the constant multiple that is already there, making that a 4, plus c1. And then for the y component, integrate 3e to the t dt, and we get 3e to the t. Nope, we do not. We get 3e to the t plus c sub 2. Okay, and we can solve for these constants now. When t equals 0, r prime is supposed to have components 5, 3. So 4e to the 0 plus c1 equals 5. Subtract the 4 on both sides, and we have c1 equals 1. And then over here, 3e to the 0 plus c2 equals the y component 3. And that means that c2 equals 0. So I actually was right, coincidentally. This r prime of t is going to be the vector with x component 4e to the 2t plus 1. Y component just 3e to the t, because that c value is equal to 0. Okay, so that's our r prime of t. Now we need to keep going because we're looking for r of t. So now we have to integrate this one, giving us vector r of t equal to, we integrate 4e to the 2t plus 1. So again, we can do like that mental u sub here, since the derivative of our u would be being the 2t is constant. So the antiderivative for e to the 2t is e to the 2t divided by 2 times the 4 that's already there, makes it 2e to the 2t. Then plus the antiderivative for 1 is going to be t, and plus our constant term, c1. Then integrate 3e to the t dt, we get 3e to the t plus c2. Okay, now using the fact that when t is 0, vector r is equal to the vector with components 2, 5. So when t is 0, 2e to the 0 plus c1, that has to equal 2. From right here, x component is 2 when t equals 0. So now we have c1 equals 0. And then for the y component, again, when t is 0, we've got 3e to the 0 plus c2 equals 5, that y component right here, giving us c2 equals 2. Okay, so now I can rewrite my r of t as 2e to the 2t plus 0. I don't need to write plus 0. And then for the y component, 3e to the t plus 2. Now, when we worked with motion along a line, we did talk about velocity and acceleration and how that was related to position. So let's say we have a vector valued function r of t. The components of that are f of t, g of t, where f of t is telling us the x coordinate of the terminal point of vector r. We can think of that as the position of that terminal point, the horizontal position in relation to the origin. And then g of t, that looks like a typo right there, right? That should say g of t. G of t is going to give us the y coordinate of that terminal point. So in this case, it's probably a little easier to think about the x component and the y component if we write them as x of t and y of t instead of f of t and g of t, but it does work out either way. If we graph our terminal point, x of t, y of t, for increasing values of t, we're going to end up tracing the path of a point, that terminal point, tracing a path in space, which is going to generate a curve. Early on in this lesson, we saw an image like that. So we can think of the vector r of t as a vector that represents the position of an object at any given time. So we're going to call that vector r a position vector. It's a position vector. It gives us the x position or horizontal position in relation to the origin, and then the y position or the vertical position in relation to the origin. So our position vector can just be represented as the vector that has the x component, x of t, and the y component, y of t. And in an actual problem, you're not going to see x of t, y of t. You're actually going to see what the functions are. For example, you might be given this vector, t squared plus 1, comma, 3t. And you might be told that that is a position vector. So then we know x of t is that x component, t squared plus 1, and y of t equals the y component, or 3t. But in general, we can write it just as x of t, y of t. So then the velocity, think about the relationship between position and velocity. We know that velocity is the derivative of the position function. And so here, the velocity vector is just the derivative of the position vector. So we can write our velocity vector as x prime of t, y prime of t. Then similarly, think about the relationship between acceleration and velocity and position, right? Acceleration is the derivative of the velocity function, which is the derivative of the position function. So acceleration is the second derivative of the position function. So we can write x component x double prime of t and y component y double prime of t. Now let's think about speed. When we were working with linear motion, just horizontal motion, how did we find speed? Well, when we first started talking about motion, we defined speed as being the absolute value of the velocity. The absolute value of the velocity. And we thought about that graphically, right? How do you take the absolute value of the velocity graph? So I'm just going to write v of t here, absolute value of v of t. That's how we have defined speed for linear motion. If we want the absolute value of the velocity graph, we know we can take all of the negative part of the graph, so all of the part that's below the x-axis, and reflect it up across the x-axis, and that's going to give us the speed graph. So here, because our position is represented by a vector valued function, we have a similar kind of relationship. The speed is still going to be the absolute value of the velocity, but now it's a velocity vector. Velocity vector. How do you take the absolute value of a vector? What does that even mean? Well, absolute value of a vector refers to, and you can call it the absolute value, but it has another name. Actually, it has several names. We can call it magnitude. The magnitude of the vector, the length of the vector. So when you refer to absolute value of any vector, it means the magnitude of the vector. Now, how do we find the magnitude of a vector? There's a couple ways to think about that. Let's just imagine we have some vector. It doesn't really matter which quadrant I place it in. Let's just say here's our vector right here, right? So we can always, unless our vector is lying on one of our axes, make a right triangle. That goes back to the x-axis here. And if we make a right triangle, we can think of this distance as our x component. This horizontal distance is our x component. And this is our y component. And then to get the magnitude of the vector, we just need to know the hypotenuse, the length of that hypotenuse for that triangle. How do you find the length of the hypotenuse? Well, you could use Pythagorean theorem, right? Leg squared plus leg squared equals hypotenuse squared. So we want square root of leg squared plus leg squared. Or another way to think about it is we know this point is 0, 0, this initial point, 0, 0. And we also have a terminal point. So now you can write the coordinates of that terminal point and just find the distance between the 2 points using the distance formula. It's going to end up looking the same either way. To find the magnitude of the velocity vector, we want the square root of the x component squared, and the velocity vector has x component x prime of t. So x prime of t squared plus y prime of t squared. So square root of all of that is going to give us the magnitude of the velocity, which we can also refer to as speed. Now this formula might look familiar to you because we did very recently work with a formula where we took the square root of dx dt squared plus dy dt squared. X prime of t is just a different notation for dx dt. And that formula involved arc length. So we're going to see how that relates now to total distance below. What is or how do you find total distance? If you remember when you were working with linear motion, how did you find total distance? It's a little easier to find net distance. To find net distance, you just set up an integral on some interval from a to b. And what is it we're integrating here? If we want net distance is just change in position. So we want to integrate the velocity function to get change in position. That's going to give us net distance. If we want total distance, how do we alter this? We have to take the absolute value of the velocity to get total distance. So here with planar motion, we have a velocity vector instead of just a velocity function, a velocity vector. And how do we take the absolute value of a velocity vector? Well, we saw that just above when we were looking at speed. So the way we're going to find total distance with our vector valued functions is to integrate the absolute value of our velocity vector, which is the square root of x prime of t squared, which you could also write as dx dt squared, plus y prime of t squared with respect to t, so dt. So now let's answer some questions about a particle that is moving along a curve. We have a vector valued function, and this vector valued function represents the position of the particle at any time t, and we do have a restricted domain for t here. T is greater than or equal to 0, so we'll keep that in mind. The first question asks, is the particle moving to the left or to the right at time t equals 2? So stop and think about how you would answer that question if this was linear motion, if it said the particle was just moving along the x-axis, for example. Is it moving to the left or to the right? So to answer those linear motion types of questions, we need to think about the velocity. Is the velocity positive? Is the velocity negative? But because our position is defined by a vector valued function, our velocity is also defined as a vector valued function. So what does it mean to say that a vector is positive or a vector is negative? What would that even mean? Or are we asking that question in the right way? So it's a similar idea, but we have to think about it slightly differently. Is the particle moving left or right? Remember that our vector valued function separates the horizontal component and the vertical component. So to figure out if the particle is moving left or right, we only need to focus on that horizontal component. We don't even have to consider the vertical component of our vector valued function. So we're just going to look at that x component, that t cubed minus 6t squared in our position function, and work with that. Now we are going to need our velocity vector. So let's go ahead and find that. And to get our velocity vector, we know that we're just taking the derivative of our position vector. So the x component there, 3t squared minus 12t. And the y component we don't need for this first question, but I don't know, we might need it later on. The y component would be negative 2t plus 8. So there's our velocity vector. Is the particle moving to the left or to the right? Let's go ahead and just figure out if that x component, so x of 2, is positive or negative. X of 2 would be, let's see, 2 squared is 4 times 3 is 12, minus 12 times 2 equals negative 12. And negative 12 is less than 0. Therefore, we can conclude that the particle is moving left. Is moving left at this specific time, at t equals 2. Part B, find the velocity of the particle at t equals 2. So here it's just referring to the velocity vector. We need to find v of 2. Oh, and I see a notational error, right? the x of 2 that I wrote here really came from my, well, I guess I used x because I was thinking the x component of the velocity vector, but just to avoid confusion, let's call it x prime of 2. Okay, find the velocity of the particle at t equals 2. So now we're going to substitute t equals 2 into our velocity vector. So the x component is going to be 3 times 2 squared, that's 12, minus, well, I guess we already found that, right? We already know that that's negative 12. And then we're also substituting 2 into the y component there, so there we get negative 4 plus 8 is a positive 4. So there's is the velocity of the particle when t equals 2. Part C, at what points is the particle at rest? Justify your answer. So at rest, what does that mean? Well, when we were dealing with linear motion, at rest meant that the velocity was 0. So can I phrase that in the same way? Can I say here it's going to be when the velocity vector is 0? Well, that doesn't sound quite right because the velocity vector is a vector and 0 is a number, it's a scalar, and a vector doesn't equal a scalar. So we have to think about it slightly differently, but it's still related, right? If our particle is at rest, then there is no horizontal motion and there is no vertical motion. So that would mean that both of the components in our velocity vector should equal 0. Both of them should equal 0 for the same value of t. So we can't really say that the velocity vector equals 0. What we can say is that the velocity vector is equal to the 0 vector. And it may sound like a silly thing, but the vector with components 0, 0 is called the 0 vector. So we would set our velocity vector equal to the 0 vector and solve for t. Okay, and that would mean that the x component has to be 0, so 3t squared minus 12t equals 0. And simultaneously, negative 2t plus 8 equals 0. Now, it's entirely possible that we will solve these equations and get different solutions for each of the equations, in which case we could say the particle is just never at rest. That's a possibility, right? So, okay, equation on the left, we can factor out 3t, and we get two solutions here, t equals 0 or t equals 4. Okay, then from the y component, we solve here, and we get t equals 4. So we're only going to consider the solution that works for both the x component and the y component. So just one t value here, and that would be when t equals 4. Now the question says at what point is the particle at rest. So we do want to find the x component and the y component at that time t. And we need the position vector for that. So r of 4 equals, and we will sub 4 in for t into r of t. So we've got 4 cubed is 64. 4 cubed is 64 minus, there we have 16 times 6. That's 60 and 36 is 96. 96. So that is 64 from 96, 32. And then subbing 4 in for the y component, that's going to be negative 16 plus 32, which is just 16. Negative 32, 16. Okay, and still, this is the position vector. It's asking us at what point. So we would write our point as a point with coordinates negative 32, 16 for our final answer there. And then find the total distance traveled from t equals 0 to t equals 4. Total distance traveled on this interval, we want to integrate the absolute value of the velocity. And because this is a vector valued function, that means we are integrating the square root of dx dt squared plus dy dt squared, or x prime squared plus y prime squared. And the x prime and the y prime we've already found, that's in our velocity vector. So that would be 3t squared minus 12t, that's x prime, so that gets squared, plus, and then the y prime, negative 2t plus 8. That gets squared as well. And integrating with respect to t. Okay, and then we will just integrate that using our calculator, which is going to give us about 37.580 for total distance. And do we have units here? We do not have units here. For a critical thinking question for this lesson, explain the differences between motion along a line and motion along a curve. So in that last example we just looked at, we did talk about some differences, right in part A. Is the particle moving to the left or to the right? The way that we think about that, or at least the language we use, depends on if we're describing linear motion or if we're describing planar motion there. And how did we determine where the particle was at rest? Is that different for linear versus nonlinear motion? Total distance traveled. Do we have to think about that in a different way if it's linear versus nonlinear or planar motion? And interesting to think about if we do have just motion along a line, let's say horizontal motion, could we still write that in terms of a vector valued function? Like everything we've done here with vector valued functions, would that still work? Is linear motion just a special case of planar motion in general, or do we really have to treat those as two separate things? Okay, so something for you to think about as we wrap up this lesson. Thank you for tuning in. I will see you next time.